Hello, everyone, and welcome here today. My name is Shelby Breger, and I'm one of the founders of Conduit Tech. Our main focus of today's webinar, hosted by MeasureQuick, is one near and dear to my heart: HVAC system design, and specifically heat pump design, the cornerstone to any successful HVAC install. In fact, one Department of Energy study found that on average, systems were oversized between 33 to 48%. And we all know the challenges of oversizing, whether it be short cycling, enhanced wear and tear on systems, and lower efficiency and lower comfort. So today, our two experts will cover the building envelope, its impact on system design, as well as tackle the difficult question of how to build the best solution for a home, whether it be a cold climate situation or something else. This is more content in here than you could ever fit in an hour, but our two speakers, Anthony Maynor and Jeremy Begley, are going to do their very best, and we could not have better experts to do so. I personally have been grateful to have the opportunity to learn from each, and so with that, I'll introduce each. Anthony Maynor is a partner at Right Tech HVAC. He has owned and operated a successful HVAC business, has a degree in heating and air conditioning, is a NATE certified technician, and has a master license in multiple states. Anthony serves on the HVACR Industry Advisory Committee for Wake Technical Community College, and also the Technical Services Committee for the Air Conditioning Contractors of America. I'm also thrilled to introduce Jeremy Begley, who is a seasoned expert in high-performance HVAC design, particularly for single-family and multifamily buildings. Jeremy began his career at Cincinnati, where he introduced innovative models for home performance contracting, and since then has founded HVAC Performance, a consultancy focused on residential and light commercial testing and balancing, HERS ratings, BPI energy audits, and LEED home ratings. He is also the founder of HVAC Design Partners, a venture focused on high-performance HVAC design, testing, and commissioning. So without further ado, I'll hand it over to Anthony and Jeremy to lead the next hour before we come to Q&A around 12:10. So to kick us off, Jeremy, we're excited to hear a little bit about Manual S and a whole bunch more from you.
Thank you, Shelby. Today, I just want to do a little bit of housekeeping really quick, and then we'll get into it. Just the order of operations here today. I will be sharing a little bit about the new Manual S and some definitions. Anthony, who we're lucky to have with us, was involved in the actual writing of the new Manual S. He will be showing you a few examples of how it can be used and some of the differences that are actually in Manual S versus the old version that we're all used to using. And then we're going to have some different examples of pitfalls that you can get into when sizing inverter heat pumps. So give me 1 second here. I'm going to share my screen with you and get these slides up. All right. So what you have in front of you here is just a brief overview of some of the major changes that that went into making the new Manual S Super. It's going to talk a lot more about heat pumps, a lot more about how dehumidification can be used in conjunction with heat pumps when it comes to sizing, and they've really refined the mandatory language and gave us some new definitions and new terminology that we really need to get used to using when we're talking about sizing heat pumps and sizing cooling units in general. These are just a few little clips that I pulled out of the new Manual S that I enjoy. It's their commentary on oversizing equipment, and I just think that there's some valuable little nuggets here that they give us. One is the sizing value for all equipment is 100% of the smallest defensible value. Very important. We want to try to size to the smallest defensible value, not the largest defensible value, which even though there's been a lot of talk about oversizing uh, uh, throughout the years, it's still the go-to for a lot of HVAC contracting companies to try to defend large sizing instead of small sizing because they're very scared of callbacks. And that is something that we are working to overcome in this industry. Also, the cooling capacity should be as close to the manual J total cooling load as possible. This will help prevent humidity problems, mold or mildew, and other problems that come along with excess cooling. And the last is a statement here. It talks about there is no energy use benefit from oversizing cooling equipment because the excess cooling capacity just increases the annual energy usage because it's unnecessary, and people can be comfortable if the equipment is sized correctly instead of oversized. I love that Manuel S gave us these little flow charts because it sort of shows how my brain works when I'm thinking about all this stuff, and actually what goes into sizing in your brain when you're trying to size heat pumps or any type of equipment. This is truly the logic that you have to follow to be able to be successful in that. And I appreciate that somebody was able to take it out of their brain and put it down on paper for us to look at. I don't know that I could have logically thought through it all like this, but it is very valuable. And if you take a look at this flow chart here, you'll see in relation to heat pumps, when we get to is equipment a heat pump, it immediately goes to determine the heat pump sizing condition. That's a verbal clue. That's one of the new definitions that we're going to be talking about, the terminology sizing condition. So um, this is the once we get into the sizing conditions of heat pump, this is what it takes to actually size a heat pump correctly. This is the thinking methodology that you have to use to get to the correct size of a heat pump. It's not as straightforward as it would seem. It's actually a little bit complicated. And so we're going to work through some of this with you guys. I'm not going to read everything up there, but the, it is that if you follow the lines and follow the logic, it is the correct way to think about this stuff, especially when we get into the actual new Manual S or the proposed Manual S. Um, so as you can see, this is sort of the procedure list for sizing. It's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps to sizing a heat pump. And you'll see step 2 says when the heat pump equipment is used, determine the sizing condition. There's that terminology again. So Manual S defined sizing condition as air to air and water to air conditioners and heat pumps shall be sized for the operating condition that corresponds to the project design. And they outline, as you'll see, several operating conditions that you have to match up to what you're actually trying to size the heat pump for. And then if we get down here, it talks about the OEM expanded data. That's what we used to call it in the original Manual S. Now we're just calling it performance data. We need the performance data from the manufacturers to be able to size this stuff correctly. And here's the minimum requirements that we need. We didn't used to need this, all of this stuff, because it wasn't a thing. Like before we got into inverter heat pumps and multi-stage heat pumps and two-stage heat pumps and air conditioners, we didn't have minimum capacity and maximum capacity to look at. We just had one single capacity to look at. So this states minimum and maximum capacity for the equipment that will be installed. Some of these things we've always been looking at. Total cooling we always looked at, sensible cooling, latent cooling. When we're thinking about Manual S and thinking about sizing cooling plants and in heat pumps, we think about that stuff. But we also on the heating side, now we're going to look at minimums and maximums, something that we've never done before. So that's some of the manufacturer side of the data that we need to even start thinking about this stuff. And then we have one other definition that we really need to look at. It's active dehumidification. So what is active dehumidification? Equipment or system functions that are controlled by a sensor to regulate the control of indoor humidity. And you'll see that when we're talking about active dehumidification, there's actually 4 types of active dehumidification, but when we're using it in conjunction with sizing a heat pump, only 3 of these types are going to be permitted as the dehumidification strategy. So we have ventilating dehumidifier, which is the Santa Fe dehumidifiers are the best example of this. They are the the pioneers in the ventilating dehumidifier space. Some of the other dehumidification companies are starting to come out with ventilating dehumidifiers, but these guys wrote the book on it and they do it. Santa Fe wrote the book on it and they do it the best uh, that I've seen so far. And that is a dehumidifier, whole home dehumidifier with ports for ducting indoor and outdoor and discharge air that also satisfy the ventilation requirement for the home, the ASHRAE required ventilation requirement for the home. Then we've got dedicated dehumidifier. This is simply a whole home dehumidifier that can hook into that can hook directly into the HVAC distribution system or be ducted and be a standalone system. But the point is that it's a whole home dehumidifier and does have the ability to be ducted. And then we've got portable dehumidifier. This is what you guys know. You can go to Home Depot and buy one of these. It's an Energy Star or non-Energy Star rated dehumidifier. It plugs into the wall. You can move it around. It has a reservoir in it where you have to collect water. If you've ever messed around with one of these things, you know you can take a condensate line and run it to there, but and try to duct it to a drain or something like that. It ends up being a big hassle. These are the ones that were not listed in the acceptable active dehumidification here in the new Manual S. And then we do have this one here, and this is system function dehumidifier, an equipment setting or control strategy to use to control humidity. There's a lot of conversation going on in our industry right now about the use of reheat dehumidification, meaning in commercial reheat dehumidification a lot of times ends up being a gas fired uh, heat that is injected into the airstream to dry it out. In residential dehumidification or in residential HVAC, this ends up being heat strips that are activated. So then you got to be real careful about the amount of power that you're using when you're using this methodology, and you have to start thinking, is this a really good strategy to use in the shoulder seasons when you're not running your HVAC at all, but you still need to dehumidify the space and maintain a relative humidity set point? Is this really the best way to go? I'm not a fan of this strategy. I know that it can be used as a poor man's dehumidifier, quote unquote, and it actually can work if you're trying to use it in conjunction in some climate zones with a HVAC strategy that only uh, provides extra dehumidification when the system is not doing it. But you have to be real careful about the amount of energy that you're using with this, because you can blow the efficiency of a piece of equipment out of the water by using this strategy. And then these are the different sizing conditions. I'm not going to get way into this because Anthony's going to cover a lot of this in his portion of the presentation, but I am just going to state what these are. Standard sizing condition. This is pretty much what we were used to from the old Manual S with some changes that Anthony will talk about. And then we have variable capacity simplified method. This is also pretty much what the old Manual S told us to use or told us how to size when it came to variable speed or two-stage equipment. This is just the simplified method of that. And then we have these two in the middle, and these are brand new ways to size in terms of Manual S. And this is sort of the meat and potatoes of what we're going to get into when we talk about the new sizing stuff. Dry sizing condition is basically either you're in a climate where there's no latent load at all, it's a sensible heat ratio of 95% or better, 0.95 or better, or you're using a dehumidifier. And then there is some really cool things that you can do if you're using a dehumidifier that will allow you to be able to size HVAC equipment, either heat pumps or air conditioners, a lot bigger than what we normally would. And it allows us to do some things like pay attention to the heating load and try to find a balance point. And Anthony's going to talk about all these during his portion of the presentation here. And then the last one is variable capacity advanced, which is the most advanced way. Oops, sorry about that. The most advanced way that you can size that allows you to, what I was just talking about, find a balance point between heating and cooling and not use any or use minimal resistance backup heat as possible. The ideal is try to get the backup heat out of there. So that is the slides that I have, yeah, for right now. And I'm going to turn it over to Anthony and let him get his slides up and let him take over for a little bit here.
Absolutely. Well, thank you, Jeremy. And
You're
bear
welcome.
with me, everybody, while I try to get my slides on the screen here. All right, so hopefully everybody's seeing my slide here, just showing some basic numbers from a manual J load calculation. And I want to really start by saying that I'm by no means the manual S expert, but I was very privileged and honored to have the opportunity to serve on the committee. And out of quite a number of manuals I've had the opportunity to work with them on over the last 5-6 years or so here, Manual S has by far been the one that has taken the most time and effort. Gosh, we probably started this back in 2019, and we're close to finishing up public review and this becoming, live and available to you guys. So I had the privilege of getting to sit through a lot of meetings, a lot of conversations with some really smart people from the industry, and learned just a ton of things that honestly and frankly I had no clue about when it comes to inverter heat pumps, variable capacity systems, variable refrigerant flow, when it comes to dehumidification. So really just a lot of just great knowledge got poured into this over the last roughly 3 to 4 years. That it's been kind of a work in progress, and all I'm going to try to do is just share some highlights from that today, and of course we'll open it up to conversation. So what I'm going to do here is start out by just walking through kind of the old school, the current manual S way of sizing just a basic single stage heat pump system. We're going to talk about how we do it now, how things would work today, and then we're going to begin to relate that to how did the guidelines change in the new manual S. And I'm going to show you some excerpts from some of the charts and tables that are going to be in the new manual S, which I'm happy to say for everybody, you may want to make note of this. Once it finishes its final review, and this could happen within the next week or 2, 3 here, hopefully, what ACA has decided to do initially is make this available free on their website as a read-only version of the standard, if you will, the normative section of the standard. So rather than having to run out and buy the book right away, they're just going to make this available to everybody at no charge. So keep an eye out on their website. Keep a search for this. I honestly expect within probably the next 2 weeks or so here, they're going to make this available. So I would definitely recommend going to their website, being able to take a close look at this. So all that being said, let me just kind of walk through how would we do things now? Like if we follow the current manual S, which is still an option, what we call the simplified heat pump sizing method in the new manual S, the simplified version, is what we're going to look at now. And it's similar to what many of you as practitioners are probably already familiar with. So I just pulled some numbers from a load calc that I've done. And what you see on the screen here is a home with a heat loss of about 19,400 BTUs per hour. And then, of course, you can see our sensible and latent breakdown there as well. So when we look at sizing a heat pump for cooling only, which the current manual S, that was the only way you did it. You sized it for cooling and you hoped for the best on the heating side, which sometimes meant some really large heat strip kits that frankly, are not the most energy efficient way that we could be doing things. When people put in heat pumps, not only do they want to be comfortable, but they're thinking it's going to be a fairly energy efficient way of heating and cooling their home. And that's been kind of, spearheaded by a lot of the energy rebates that everybody's familiar with from various utilities and other industry groups. But it puts a perception in a customer's mind that, hey, this is going to be the best thing ever. I'm going to save a lot of energy. And then in reality, they don't always see that, especially if they're in a colder climate. So more to come on that. But as we start digging into talking about cooling and sizing a heat pump now, using the simplified method, the first thing I always try to point out to people is you've got to use manufacturers, what we like to call expanded performance data, engineering data. Different OEMs call it different things. But what we don't want to do is just grab plain Jane like ARI type data. We want to dig in. We want to basically figure out what is the performance of that heat pump for both heating and cooling at exactly the same conditions that I ran my manual J load calculation at. So for example, this particular house I did was in a climate where the summer design temperature was 92 and the winter design temperature was 23 degrees Fahrenheit. Well, I want to see the performance of this unit at 92 degrees in the summer, and I want to see it at 23 degrees outside temperature in the winter. And in addition to that, I also want to see the performance at the same indoor design conditions, which of course everybody knows Manual J currently is recommending 75 and 50% relative humidity, or of course a 63-degree wet bulb. So we need to go into this expanded performance data. All the major OEMs provide this in some way, shape, form, or fashion, and sort of dig into it to get the exact output capacity of that machine in cooling mode and in heating mode at the exact same conditions we ran our load at. So I always tell people we're trying to compare apples and apples here, and not two different sets of design numbers, apples and oranges. So that to me is one of the cardinal mistakes that a lot of folks that are not as familiar with Manual S and proper equipment sizing and selection tend to do. So you always want to make sure you kind of dig into that. So just to kind of cut to the chase and simplify, I've just gone to one major OEM. I pulled up some expanded performance data for a heat pump, looking to match up for that load that we just looked at. And basically, if I interpolate the data that you see on the chart here to match my design conditions in the summer, which was 92, 75, and 50% RH, you can see what I've got here in terms of performance. I've got about 17,600 BTUs per hour total cooling capacity, of which 13,990 of that was sensible, and the remaining 3,610 was latent. So how would I apply this using the current Manual S? Well, I go to my current load calculation. I say, okay, well, for cooling, I've got my sensible and my latent gain, and I want to add those together to find out what is my total cooling load. So that comes up to about 16,278. I know this is a little bit math intensive, so humor me for a minute here. But if we take those numbers, what you see in white, that at the top of the slide there, that is the load calculation numbers, the heat gain from my Manual J. And what you see kind of in dark blue down below, that's the interpolated performance data that I just derived from my OEM's expanded performance data. And then all I've got to simply do is just go in here and apply the procedure that Manual S gives us. So down at the bottom in red, it's pretty straightforward. You just take the capacity of the unit and divide it by the respective heat gain from Manual J. So if you kind of go down the line here, you'll see up at the top, our total cooling capacity for that system was 17,600. And I've divided by my total cooling load of 16,278. And what you're seeing, and for simplified wording here, is that we're oversized by about 8%. So this system's got a little bit, about 8% excess cooling capacity on the total cooling load side, which is really what Manual S is set up to focus on. But I like to look at a little bit more. I'm going to kind of skip past the sensible cooling capacity for a minute. You can still see there in the middle that we're over 100%, but I really want to jump down and put emphasis on the latent cooling capacity, because this is going to be a major point of conversation for us as we circle our way through this little webinar today and come back around to some dialogue at the end here. You can't understate the importance of the latent cooling load. You've got to make sure that your system has the capacity to maintain that design relative humidity in that home. You've got to make sure without any hesitation that your system will meet at least 100% of that design cooling load. It's okay to have some excess there, but we don't want to come up short. If we come up short, we really need to go back to the drawing board and look at different sizes of equipment to see if we can get something that still matches up for our cooling oversizing factor, but provides us that 100% or greater on the latent cooling side. If we don't get rid of that cooling capacity, we're definitely going to have issues that are going to cause us some dehumidification problems. And as many of you know, especially if you've been doing this for a long time, in most parts of the country, that latent is everything. If you're not getting the humidity out of the house, if you're not maintaining that indoor humidity at a comfortable spot, you are going to have issues, folks, not only in terms of occupant comfort, but potentially in terms of long-term health implications. Because if we get too much humidity building up in there, that can lead to some of those nasty things that we sometimes find growing inside of units and duct systems. And I've seen situations where it's actually spreading out to living sections of the home, if you will. So again, I can't overstate it enough. That latent ability to dehumidify, folks, is just so critical here. So to kind of circle back and cut to the chase, as you look at the slide that I'm showing you here, just some pretty straightforward math, and you can see that, bingo, this is a good system. It meets the load. It does what we need to do here. And I apologize, for some reason my slide is not moving, so bear with me for a minute. I'll see if I can't unshare and reshare this thing and get it to talk to me again. Kind of froze up on me there. All right, so we can see that we've got a good match here. Now, using the current manual S, this is where you stopped, and nobody ever looked at the heating side of a heat pump, which to me is a huge, point that, hey, we've got to go back and we've got to make sure this thing's not only going to cool effectively, but it's going to actually do a respectable job of heating. We don't want to run a lot of heat strips. We want to minimize that electrical demand as much as possible, give people the best energy bills that we possibly can. So for most folks, again, this is where they would stop. So what I'm going to show you now is an excerpt from the new Manual S, talking about what we call the standard sizing condition for basic heat pump systems, and for cooling systems for that matter. And basically for a single stage unit, which unfortunately makes up about 85% of what gets installed across the country nowadays, the way that the old Manual S set that up, we had a maximum oversizing limit, for lack of a better word, of 15% for a single stage, 20% for a two-stage system, and 30% for a variable speed or variable capacity system. So if you look at the top of that chart there where it says, air to air, air to water, single speed, you'll see that we've broken that up and defined it a little bit better. So the red arrow up at the top is pointing out that we now have two different sets of potential sizing limits or criteria there. This is the first part for systems up to 24,000 BTUs per hour. And there we're really talking about the cooling load, not the system capacity, but the cooling load. And then the second red arrow is for homes having a cooling load of more than 24,000. And the reason for that, you'll notice that we expanded the parameters here. For a single stage unit, instead of the old 15%, if you've got a load of less than 24,000, you can now have a factor of 1.2 or a 20% oversizing factor there. And that's not that we're trying to encourage people to unnecessarily oversize equipment, but when you really break down and look at the math between, say, a nominal 18,000 BTU per hour system, 1.5 tons, versus a 2 ton at 24,000 BTUs per hour, that's almost a 30%, roughly almost a 30% jump. And so there was a lot of loads, especially in modern construction, where, to be quite frank with you, the systems that were available really wouldn't match up and fall within that 15% parameter for a lower load type of home like this. So we recognize that concern there, and this is something that a number of people from industry brought to light as the new Manual S was coming about. So the 15% oversizing for single stage equipment still remains for larger loads, 24,000 BTUH and above. But for smaller loads, we've given, again, an extra 5% buffer there to make sure that you can actually buy an OEM package system that will fit within the criteria. So again, we go back to that smallest defensible load. We want to make sure that you can select something that, worst comes to worst, you can actually defend yourself on out there in industry. So I think that's a very important factor. I'll draw your attention down to the bottom of this chart where it talks about two-speed equipment, or two-stage might be a better word for that. But you'll notice your total cooling size factor now is up to a factor of 1.25. Now, it used to be cut off on the old Manual S at 1.2, but again, the same issue came into play. Many of the major OEMs make two-stage equipment in whole ton increments. So we started out at maybe a 2-ton, then a 3-ton, then a 4-ton. And when we don't have half-ton sizes available, you sometimes find that the load of the home versus the capacity of the equipment in those whole ton increments, you just couldn't match up a system that would fit within that 20% factor. So there appeared to be a demand and a need to expand that just a little bit to make sure that we could get systems to fit. But I always go back and tell people, at the end of the day, you want to size as close to the load as possible. We want to be as close to or slightly over that 100% mark. We don't want to have any unnecessary excess total capacity on this machine if we want to have a good, efficient system, particularly one that's going to run and dehumidify well when we're at part load conditions. And most of you guys know that we spend most of our load hours every year, something like 98% of them, at part load comfort conditions, when it's less than design temperature outside in the summer or greater than design temperature outside in the winter months. So kind of to keep things moving, kind of looking at the old Manual S again, and still something I recommend to folks to do on the current Manual S, but I'm going to show you how we kind of take the old school kind of school of thought and then relate it to some of the new terminology and the new options that are coming up here. Is we size based on cooling using this basic simplified method, but a good practitioner, a good contractor in my mind is always going to say, hey, there's more to the story here. I've got to look at the heating side of this. So once again, we go into our OEM performance data. I pull up the design performance data for the same exact heat pump that I showed you the data for there on the cooling side. And I want to kind of dig into this a little bit. And what you're going to notice is I can match up, again, my outside temperature, which is kind of down the left-hand margin there, along with my indoor design temperature, which again is 70 degrees per the normative section of Manual J. And I can see what the heating output capacity of that heat pump is as outdoor temperature changes. And you'll notice the trend here as outdoor temperature decreases on an air-to-air heat pump. Of course, the BTU per hour output capacity of the refrigerant side of that heat pump continues to decrease along with that as well. So where am I going to go with this information? So what I always advocate is create what we call a thermal balance point diagram. So just a simple piece of graph paper, and you see across the bottom, I've got outdoor temperature decreasing as you go kind of from right to left. And then across or going up the left-hand side, you'll see we've got BTUs per hour. And basically what I've done in the center of this chart right here, if you look at the orange line, my load, the 19,400, was at a design outdoor winter temp of 23 degrees. So I find my 19,400 at 23 degrees. I drop a pencil point. That's kind of where you see the yellow arrow there. And I basically make a straight line down that chart from 65 degrees at 0 BTUs per hour. That's considered to be the point of no heat loss. So probably a little bit beyond the scope of this conversation right now if you're not familiar with it. But we start there at 65 degrees, which is considered a point of 0 heat loss. I plot my design heat loss at 23 degrees. That's the 19.4. And I take a ruler and I draw a straight edge. So what that orange line represents for me here is the heat loss of the house. And you'll notice it's very linear here. The colder it gets outside, the greater the rate of heat loss for the structure. Now what I can do is I can take that performance data that we just looked at, and I can basically go in here and I can pick a few outdoor temperature data points, and I can plot that as well. So kind of that dark brown line, you'll notice again how it starts producing more BTUs per hour at a warmer outdoor temperature, and it's decreasing as the outdoor temperature is decreasing. Well, the point is where those two lines cross, where they intersect, at least in theory on paper now, that is our thermal balance point. That is the temperature where if I did a good load calc and I did all my design work and preparation correctly, I can figure out where that system should be able to carry that house down to, at least on the theory side of this, if you will. So roughly about 35 degrees is what I'm looking at here. Well, that does two things for me. So for myself as a contractor for about 23 years, I always wanted to look at this and I wanted to figure out, okay, I sized for the cooling, which is what the old Manual S told me to do. And the current Manual S does the same thing if we're following what's called the simplified method, which is what the vast majority of folks probably are going to use and run with out there. We're going to talk about the advanced method that's coming up here shortly. But I also want to go look at that heating performance. In my world, I always wanted a unit that not only fell within the sizing factors, the parameters that were given to me on the cooling side, but I wanted something that would carry that home down on the heating side, preferably into the at least the middle 30-ish range. Then I knew I would have a heat pump that was going to perform reasonably well and efficiently for both heating and cooling that house. And as Jeremy mentioned earlier, I really want to make sure that I'm going to minimize the need and the use of any unnecessary excessive heat strips. So if you look to the left of my thermal balance point, as I head towards 23 degrees, you guys are going to notice there's a gap forming there. There's a triangle that's forming. And that's the point where if I use the old method or the current simplified method, I've got to make up that amount of heat somehow. That's what we need auxiliary or supplemental heat for. So if we're going to design a system where we're still planning to include some form of supplemental heat, this allows me to see what that need is. So for this particular scenario, if I did the math, and I realize I'm kind of accelerating through a lot of fine points here because we are limited on the amount of time we have. I would see that I've got to make up a gap between 35 getting down to my design of 23 degrees of approximately 8,100 BTUs per hour. And I need to figure out, well, what size heat strip would let me accomplish that? So if I've got 8,100 BTUs per hour, I need to make up. There's a little watts to BTUH conversion formula I've got on the bottom right of the slide that you can hopefully see there. So I take the BTUs per hour and divide it by 3.413 to convert it over to watts. And I'll see that I need roughly about 2,400 watts, and about the smallest nominal heat strip you're going to find that maybe accomplishes that's about a 2.5 kW nominal heat strip. So if I were only sizing to provide supplemental heat and nothing more, then that would be approximately the minimum size electric heat strip that I should put in. So I point this out because a lot of folks go out and they say, oh, I've got a 2 or 3 ton system. Give me a 10 kW heat strip. Well, there's a little bit more science behind it, a little bit more accurate way that we can look at this as a designer to make sure that we're not unnecessarily oversizing the heat strips. Because as all of you well know, when those heat strips come on, the bigger they are, the more amp draw, the more current we're consuming, and the more that watt meter spins and the more it costs people in electricity. Now, there's also a school of thought out there that, okay, I see what you're saying, Anthony. I can just size for the supplemental heat, but if I'm putting heat strips in here anyway, well, maybe I want to also consider being able to provide some degree of emergency heat should something break down, should something go wrong on the middle of a cold snap and I can't get a tech out there immediately. I can try to maybe keep that customer reasonably warm. So again, same scenario as always. Manual S recommends not sizing emergency heat for more than 85%.
Looks like Anthony might have frozen for us here. Jeremy, are you able to jump in? Oh, Jeremy, you're still muted.
Mute. I put 2 mutes. I double checked myself. I'll tell you what, I don't have access to Anthony's slides. I know that he was going to take this emergency heat line of thinking and take it into how we get away from emergency heat using the methodology that is in the new Manual S. And I see a comment here in the comment section. Someone's asking about, they thought this webinar was geared to cold climate heat pumps, and it is. We just haven't got there yet. Anthony was taking the long way around because he wanted to show the path that the standard took to get to the sizing for the cold climate heat pumps and what that looks like. But what I'm going to do is I'm going to go ahead. I do have some examples here of cold climate heat pumps and some of the sizing pitfalls. I'm going to go ahead and jump into that, and then we can get back to the standard at a later date, or maybe when Anthony gets his feed fixed here. And I can talk about the standard and some of the sizing methodology a little bit, but I was going to let him do that a bit. That was sort of our plan, but let's just go what we got here. Give me 1 second to get this slide. Anthony's back here. Do you want to sort of finish out your thought there, Anthony?
Yeah, sorry guys, I don't know what happened there. I got dropped, but let me try to reshare that screen and I'll wrap this up, Jeremy. Apologize for that, everybody. The wonders of technology here, sometimes they fight us. So hopefully we'll get back to that slide. And I'm not sure quite where I got cut off, but talking about size and heat strips. And again, Manual S gives us a pretty broad amount of leeway on heat strips, anything from about 95% of our target load all the way to 175%, which to me is pretty extreme. So I like to look at maybe the sensible heat equation, and I'm just going to, again, to catch us back up, accelerate through this. I can do a little bit of basic math, and I can figure out approximately at my nominal airflow, whatever the size of that system is, what my, on paper at least, what my temperature rise is going to look like. So this way I kind of have an idea what's the smallest heat strip I could put in here, save them energy if I'm even using heat strips. And on the flip side of that, make sure that if I ever needed to use it for, say, an emergency mode, if that's my train of thought, that I can do a respectable job of raising the air temperature, what will actually feel like heat for the customer. So to me, I think that's an important thing to consider. So here we go and diving into the fancier stuff here, the new Manual S, and I want to talk about variable capacity equipment sizing, because this is the new stuff that everybody's looking at. And when you start talking about, hey, we're in a cold climate, we want to do cold climate heat pump size, and we want to use variable capacity stuff here. We don't want heat strips. We want the heat pump to be the sole source of heat. How are we gonna make that work? Well, this chart here kind of summarizes that. I know it's a lot to digest and look at it, so I'm going to let you just kind of peek at it for just a minute. And then Jeremy and I'm going to run through it. We'll talk more about it, but we want to dig into a little bit of the why. And this was driven by a number of major OEMs that obviously produce multi-head mini split equipment, one-to-one mini split equipment, unitary systems, again, variable capacity, that type of stuff. And you'll see that when we come to variable capacity systems, it's broken down into two major segments here. You'll notice the first segments up at the top, it says simplified, right? Simplified cooling only, simplified heat pump. And what we're saying here is that the cooling requirements we talked about still apply. So if we've got a load, say, over 24,000 BTUs per hour of the home, we can oversize by no more than 1.3 or 30% on the cooling size, but we also want to look at the heating size factor here, and we want to see what that looks like. So now we're going to look at heating and cooling, as well as minimum compressor heating size factor, and see what some of that looks like as well. So if I skip ahead a slide, what I'm showing you are some excerpts and the footnotes to that table. When we're looking at step 2, the simplified procedure for heat pump size limits, it basically spells it out for you. We've got to meet the cooling only size limits for cooling, and note the word and, the heating capacity divided by the heating load, which again is your basic Manual S criteria to determine sizing factor, must be equal to or greater than 1.0. This means that we're providing 100% of that output that we talked about there. But we also need to look a step further. We need to figure out what is the minimum compressor heating capacity divided by the heating load and make sure that it's less than 0.8. So again, we're just going to go into our performance data. I'm showing you here full capacity from a major OEM on one of their variable capacity heat pump systems. And I'll look at it again at minimum capacity here. And again, minimum capacity for heating. So I get my two numbers based off of this. And again, I go back and I basically apply the same math logic that we've been looking at before. And in this particular example, which I'm applying to the same house, you'll see that that heat pump is only meeting 99% of the load. And it asks for 1.0 or 100% of the load. And again, I know we're limited on time here, but many of you are probably used to Manual S, and you'll know that we're allowed to use airflow adjustments to help massage the output of that unit a little bit. So if we bump our fan speed up, our target fan speed a little bit, we can normally get about a 1 to 2% bump up in sensible heating output from a heat pump. So I feel pretty good in saying that that heat pump can meet 100% of the load. But I also need, this is the new part, I need to look at the minimum heating capacity output, again, at design temperature, 23 degrees, which now is only 10,886 BTUs per hour. And you'll see that that's meeting about 56%. And what the Manual S is telling us here is that it should be less than 80%. And this is kind of a weird concept to understand, but a couple of the major OEMs really push this. They're finding a lot of failures in variable capacity, inverter-driven heat pump systems. They're finding a lot of premature compressor failures. And what they're finding is that folks are going out there and saying, oh, it's a variable capacity system. It's an inverter. If I need a 2-ton, why don't I just put in a 3-ton? Then I know I got plenty of capacity, especially for heat. And in cooling, it will just ramp down and it'll run at a lower capacity. Well, that's true, but not so much where we want to go, because a couple of negative things happen that immediately come to mind. Number one, and Jeremy will talk about this more towards the end, with many OEMs, when you get down to the minimum end of their operating capacity, particularly for cooling, you end up in a scenario where you don't have latent capacity. You may have very minimal, if not any, latent cooling capacity out of these systems. So what we're trying to do here is we're trying to make sure that the system stays loaded. It's ramped up where it spends most of its operating range hours, if you will, loaded up where it's in the upper percentage range of what it's allowed to ramp up and down to. We don't want it so oversized that it spends the bulk of its time running down at minimum capacity, because then we run into not only dehumidification issues in the summer months, but we also run into scenarios where we have oil return problems because of the lower RPM of the compressor. We're not getting a good oil return back to the compressor. And that, of course, can lead to compressor failures and things that we want to obviously avoid out there. So last but not least, because I need to hand this back off to Jeremy here, if I can get my slides to advance. And of course, they don't want to. So I'm going to stop sharing screen, Jeremy, and let you run with it from there.
Hey guys, good to see you again. I'm just going to address a question really quick because I think it's important to talk about, and it sort of puts a pin on what Anthony was talking about there. David's asking us how does this work with the house where a heating load is 3 or 3.5 tons? Thank you for that, my back screen guys there. How does this work with a house where the heating load is 3 or 3.5 tons and the total cooling load is 1 or 1.5 or 2 tons? This is the perfect example of this ratio of how we can really apply some of these new sizing methodologies, and how we have been doing it for quite a while with these inverter heat pumps. Something like that. Yeah, I'm going to show you a slide in a minute here, but you're going to have a turn down that can facilitate. And when I say turn down, that's a minimum cooling capability or minimum heating capability of the heat pump versus the maximum heating capability of the heat pump or maximum cooling capability of the heat pump. If we size towards that heating load, I like to say towards, because sometimes we might not get all the way there, but we try to, like Anthony said, service 100% of the heating load so we don't have to put backup heat strips in. If we get to let's say we have a 3.5 ton heat pump and it's a 2-ton cooling load or 1.5-ton cooling load. Most of the time, as you're going to see from some of the examples I'm going to show you here, we're going to be able to size at 3 tons with these inverter heat pumps and have a cooling load that's going to have a minimum cooling capacity that will also service the entire cooling load. And that is what we want to do. That's the gold with these inverter heat pumps. That is where they're super valuable at. We're able to try to, on the back end, hit that cooling load, and on the high end, hit that heating load, or some places it might be vice versa. Now, I've seen a lot of questions too about what do we do if there's extreme swings in the heating and cooling load, and it's not the house or something like that. So one thing to think about with that is let's make the house meet the heating load and the cooling load and bring them closer together. Like if you have those extremes, a lot of times, 99% of the time, it's not as temperature or climate driven as you think it is. It is the thermal envelope of the home, because if we have a good envelope of the home, the better the thermal envelope gets, the closer to equilibrium we get between the heating and the cooling load. So if we can improve the thermal envelope of the home, we're going to be able to use these inverter heat pumps a lot more efficiently the way that they're designed to be used. The farther we get away from, especially in like a heating dominated climate, if we have a house that's not thermally sound, that heating load is going to be way jacked up, and it's going to be almost make it impossible to use these inverter heat pumps the way that we want to without putting heating strips in. So it is essential that we continue to pay attention to the thermal envelope of the home when we're thinking about this stuff, because it makes it a lot easier to make these things shake the way that we want them to shake. Now, give me 1 second here. Let me share my screen with you guys. Oops. First, I got to share the screen. I forget the order of operations here. Share screen window. Yep. There we go. All right, so let's take a look at a few examples. This is a TempStar inverter heat pump, and it's not a cold climate heat pump. It's just their TempStar right now does not have out a cold climate heat pump in the ICP brand. As far as I know, Carrier and Bryant are the only two that have out high heat, is what they're calling them, high heat pumps. But this is a good example to look at. So this is an inverter heat pump, but if you look at the cooling capacity minimum maximum, you see we get some pretty good turn down there, 1.5 tons, 2 tons, 1.5 ton. We can size it all the way to 18,000 BTUs and still service anything as low as a 5,400 BTU cooling load in the cooling season. So we can get a nice range there. And you see most of these sizing parameters, 1 ton, 3 ton, 2 ton, 4 ton, they all have a nice spread there of what we can get to. But if we take a look at the heating range on this, we're not getting full capacity at these lower temperatures like we need to be able to not install backup heat on this thing. So even though it's an inverter heat pump and the box looks exactly like the high heat pumps and the hyper heat and the different names that they have out there for these ones that can go to the low temperature ranges, this heat pump in particular is just not doing that. So there is not a lot of value when it comes to a heat pump. There is a lot of value, but there is not the value that we are looking for when it comes to being able to get away from the heat strips and to size something that's super efficient. And then you also see, I'm going to talk a little bit more about this in a minute here, but you see the COP, which is the efficiency ranging, actually drops as the temperatures get colder outside at 5 degrees. This one's at 1.9. That's not terrible. One thing I do want to mention though is on the last webinar, I think I heard some people talking about COP, or maybe it wasn't even our webinar, a different webinar, but COP in terms of furnaces, like you cannot it's not a straight line. So you can't take a 95% furnace and say that's a COP of 0.95 or something like that, because it's actually not. It's a little bit higher than that. When you do the actual math, coefficient of performance is not a straight line. So like what I'm getting at is down at 5 degrees, 1.9 is a lot closer to a 95% furnace than you may think it is when it comes to coefficient of performance and efficiency. If you do the math and you actually get your graphs and your charts out that it takes to actually calculate COP, it's not a straight line, it's a curved line. I just want to make sure that we're clear about that. Now let's look at this. This is the Mitsubishi Hyperheat. Now this is one that goes down to cold temperatures, 2-ton system here. And so, actually, let me back up. I'm sorry, guys. I'm getting a little bit. There we go. Getting a little bit ahead of myself. Mitsubishi 2-ton single zone hyperheat performance chart. Okay, so this couple things I want to point out here. First off, this particular air handler has a selectable external static pressure of 0.3, 0.5, or 0.8 with 3 fan speeds to go with it. So guys, we can get down to some pretty low BTU equipment and still push the air around the way we need if we pay attention to the air handlers here. Like all these inverter heat pumps have various air handlers that can be matched up with them. Some have the static pressure or the ass behind them to push the air where we need it to go, and allows us to do some pretty cool designs with our ducted systems and still be able to get the air where we need to go. And then some of them are not going to do that without paying attention to very close attention to your duct design. So just be aware of what heat air handler you're matching these up with. And then you'll see here, this does have the capacity to put electric heat strips in if we needed to do that. There's some very cold climates that code requires you to put in resistance backup heat or some kind of backup heat no matter what. If you're installing a heat pump, it doesn't matter what you say or what the programs say. The local code does require you to do that. They require it because they get to extreme temperatures where these heat pumps, no matter what they are just not going to work right now. But you get a lot of benefit out of them. So let's look at a few things here. One, we see that this particular heat pump, 24,000 BTUs, it has a minimum capacity of 8,800 BTUs. So it can turn down all the way to 8,000. So we can size for a 24,000 BTU heating load and something under a ton on a cooling load. So there's a lot of value of being able to do that as long as we pay attention to the other factors. Now, one thing I want to point out here too is the efficiency ratings of these things. So you're going to see a lot of times they have maximum capacity and rated capacity. Rated capacity is what you're going is where you're going to get the rated efficiencies of the system at. Maximum capacity is what they can do. When they give you a rated capacity and a maximum capacity, they're telling you, hey, this heat pump can get full capacity at this particular or close to full capacity at this particular temperature, but at the maximum capacity, you're not getting the same efficiency levels. We haven't done the testing to make sure that you're going to maintain these efficiency levels at this maximum capacity. And you see, as we get down here to to the lower heating, they're no longer giving you rated capacity because they don't have it. But then you actually will get a footnote here. This says COP at 5 degrees at maximum capacity. They go to rating it at COP because it's not going to be the same as the SEER ratings here. You're going to have to look at COP, and those are two slightly different ratings. So this one here actually is at 1.6. A COP of 1.6 at 5 degrees, and then at negative 13, where the maximum capacity is still allowing you to get 18,400, we don't have a rating at all. There's no efficiency rated at that negative degrees when you're getting maximum capacity, because at those low temperatures, we don't care about the efficiency. We just want to stay warm, right? So for right now, that's how it is. I think that as the technology progresses, we're going to start seeing ratings at these lower temperatures, but we're just not there yet. And that's something you need to be aware of when you're sizing and specifying these pieces of equipment. Now, let's look at a single stage hyperheat, a single zone hyperheat at 0.75 BTUs, or 0.75 of a ton, which is 9,000 BTU output, nominally rated at 9,000 BTU output. Let's look at what we can do with this. Again, a very specific picture. I want you guys to be aware. Here's another option that they have. You know, Mitsubishi, Midea, some of these companies have started coming out with these. Mitsubishi calls them Easy Fit, and they fit right into a recessed right into a 16 on center joist space with no room above. There's no headroom. Everything comes out the side of it. It is a beautiful thing. I use these things a lot in the multifamily world for small spaces, or, you know, like a bedroom and a living area. You put one in the bedroom, one in the living area, and you can service the whole entire thing from above. And it really gets away from things hanging on the wall, which a lot of architectural professionals do not love. Homeowners don't love it. Putting it on something that they have to hang on their wall. Even though when I first, like 10 years ago, 15 years ago, when I first started going to these classes, I remember, or looking at these inverter heat pumps, I remember going to a Fujitsu training class for sales. And the guy said, when you're sitting at the table, ask the homeowner to turn around, or without turning around, tell you what's hanging on the wall. He's like, I guarantee you none of them can do it. It's because after something's been hanging on your wall for a while, you forget it's there. So that's just a little caveat of maybe you can get the ductless stuff that hangs on the wall to go a little bit more than it normally does. But let's look at a couple things here. So first off, maximum capacity 9,000 BTUs, your minimum capacity 4,800 BTUs. So that's a nice range of cooling capacity there that you have for this particular piece of equipment. These 9,000 BTU, whether it's the ductless or the ducted systems, they work well in multifamily applications like apartments and things like that, because these loads are that small. If you remember the webinar from last week, we talked about, or from the first week that we did this, we talked about some apartments, like none of them had a load over a ton. So what were we going to do? This is perfect for that type of application. These are under a ton. They get way down on the cooling load, so you can service those part load conditions pretty well. One thing you have to pay attention to is moisture removal is rated at full capacity. So once these things start turning down, what do you think's happening to the ability to remove moisture? It's proportional, just like any other piece of equipment, 70-30, where about 70% of your capacity is going to sensible and about 30% of your capacity is going to moisture removal. And so that capacity drops as the sensible capacity gets down to 48%. Then you're at about 30% of that or less with your moisture removal. So it gets very, very small. So you have to pay attention to that when you're using these smaller pieces of equipment, else you're going to get into trouble with your dehumidification. You're going to start having moisture problems and not know where they're coming from. And now let's look. This is where it gets real fun, guys. Let's get into Mitsubishi 3-ton multi-zone hyperheat heat pump. Now, these multi-zone, there is so many different pieces of information that you have to pay attention to when you are sizing multi-zone stuff. So first, note right off the bat that it's going to give us, even though some of this stuff stays the same, some of it also changes depending on what piece of equipment. Notice you have cooling, and heating, non-ducted, ducted, or mixed. There's sometimes different capacities and different parameters depending on what configuration of heat pump you're using. So you really got to go into the data and pay attention to this stuff. You got here your maximum capacity. It's a 3-ton heat pump. And then notice this, you have a minimum capacity of 15,000 BTUs. That's almost a ton and a half of cooling capacity that you're getting down to, but it's only a ton and a half. So think about if you have a 9,000 BTU head coming off this somewhere, 6,000 BTU head coming off this somewhere, and a 12,000 BTU head coming off this somewhere. Depending on what's calling for cooling at what time, you may be running that 6,000 BTU head and only ever getting 6,000 BTUs out of it, nothing lower. Or you may be running that 12,000. Think about that, a whole ton of cooling you're running at all times. If you don't pay attention to what you're doing, these things can easily, when you get into the multi-split systems, easily turn into singles, essentially what is a single zone piece of equipment that has no turn down, and it's just going to turn on and off. And for that zone, you may end up or it's going to modulate at that same temperature. Basically, the same thing is turning on and off at that same exact BTU output, and you might end up getting moisture problems over there, or you might end up not getting any kind of cooling turn down at all to service the part load conditions, what you're trying to achieve with these things. So you have to be aware of that. And then when you get into matching these up as well, you have to look at the engineering data, because when you get one to many like this, you end up losing capacity on some of these things. So like if you got it 9,000 BTU and a 12,000 BTU coming off this somewhere, and they all call at the same time, you're not getting 9,000, 9,000, 12,000 out of them. You're going to get something less than that. You're going to get around 8,500 BTUs or around 11,500 or 11,000 BTUs out of those indoor heads. So you have to pay attention to that too. You're not always getting the same capacity as what's rated as the maximum here on this outdoor piece of equipment. And then you see here that it's the same deal here with the efficiency. Look at the difference in efficiency depending on what combinations you're using. It is quite significant, and it does come into play depending on what you're using these things for, especially in the program world when you're trying to install certain meet modeling requirements and certain efficiencies to meet the model. You really got to pay attention to what you're getting out of this, because look at this. You're non-ducted. If everything's non-ducted, you're getting 23 SEER out of these. They're rated at 23 SEER. If everything's ducted, you're only getting 18 SEER. That's a significant difference. If you got a mixture, what just happened? Oh, hold on. Let me get the slide back, y'all. Sorry about that. If you're yeah, you're only getting 20, so that is a significant difference. And then look at the seat coefficient of the performance. Not a big difference, but still it is. But I want you to notice something else here. Look, Energy Star certified. Guess what? Energy Star did not certify. They did not
Jeremy,
certify.
slides
Yes,
aren't
yes.
back yet.
Oh, they're not? Jesus, hold on. I guess I got to stop sharing and all that. Yep. Hold on, guys. Sorry. I'm technically inept today. Live stuff's always fun. Live TV is a joy. Just ask the guy who
All right, we're back.
live TV. Okay. There we go. Okay, so look at my highlight at the bottom there. I'm sorry, guys. SEER, you can see the difference in SEER. Now look at the difference in coefficient of performance, but look at the big no in the middle there where it says Energy Star certified. If you're mixing ducted, non-ducted, Energy Star is saying we're not putting our stamp on that quite yet. They haven't proven that they can maintain these efficiencies at all times at the rated condition. So that's just all stuff to be aware of, guys. There's a lot of nuance when you're dealing with these these heat pumps. I think that is the end of my slides. Let me escape there. So what I'm going to do now is I'm going to bring Anthony back up, and I'm going to let our moderators pick some of the more pertinent questions, and me and Anthony are going to play Let's Answer Questions.
Perfect. Well, thank you so much, both of you, for such great content. There was a ton of questions coming through. We will not be able to answer them all, but we're going to do our best to make it through some of these. So, question from Timothy Naher: how do we size proper latent removal? Especially, don't you need to know the air leakage of that home to be able to size that latent removal properly?
Do you want to go, Anthony, or?
I can approach it. So, that's really going to fall back on your manual J and how you input that information on infiltration and any air leakage into your load calculation. And of course, the most precise way of doing that is if you actually have blower door test data for the home, and you can figure out the amount of leakage, assuming it's uncontrolled leakage. We're not bringing this in as ventilation air, let's say. Otherwise, unfortunately, the fallback, the simplified method of manual J is just sort of a best guesstimate at what our infiltration rate is, right? Like how well is this house built? So, Jeremy, I don't know if you want to tag on to that a little bit further, but you to do it accurately, you're going to have some kind of information. You're going to have to use the kind of standard default assumptions there in manual J.
Yep. So I'll just speak from personal experience how we approach this. We always use the blower door sizing. Even if we're using a predicted load, we still use the blower door sizing. We have began to understand how houses test out, for lack of a better word, with different construction materials. And so we have a chart that we use internally that we know if it has exterior insulation on it, exterior rigid insulation, there's a range of ACH that house is probably going to test in. We know if it's not using exterior rigid, there's a range of ACH that the house is probably going to test in, and we stick pretty religiously to designing to those numbers. So like, for instance, exterior rigid insulation, we know it's going to test between 1 to 3 air changes. So we use 3, and if we know the builders really well, we'll use something even more dialed in, like 2.5 or 1.5 or something like that, depending on what they test at. And we'll design to that because that gives us the best chance of predicting the latent load and being able to design to that latent load. this is a really good question because yeah, the air leakage is one of the biggest deals when it comes to latent load besides the internal loads. And the internal loads we can predict pretty well, especially if we know who's going to live in the house and they're going to use the downstairs as a, gymnasium or whatever, something like that. We can put that in the load and account for that. But when it comes to air leakage, you have to come up with some kind of way. If it's not an existing home and you can't go out and put a blower door on it, it's my advice to come up with a way to be able to try to design to some kind of predicted air change number, because the other way is just guessing. I mean, it's a WAG, wild ass guess, when it comes to actually predicting if the house is tight or loose or whatever those old metrics are. Like, I have thrown those things totally in the garbage and I don't use them at all. But that's my personal design methodology.
Thank you both. So our next question is going to come from David Horton. If we want to size the smallest defensible load, how do we address devaluing the insulation or other variables that may not perform as rated?
I would say verified installation. So like the best way to do that is to have a rater go out and verify the things that are being installed so that it will perform properly. We can't always be 100%, but we also can't base our load on guesswork of what if this insulation doesn't work like they're saying it works, then what have we done? Like, we've designed something that may or may not even be to that house. If we design to what's being put on paper and what's in the house, at least we have something we can stand on and we can go back to and try to work it out. If it's not performing like it's supposed to, we have a starting and an ending point.
Fantastic. Anything that you want to add to that, Anthony, before we?
No, Jeremy is by far an expert on the topic, and I think he's addressed it very well.
Awesome. Well, it sounds like the answer you just gave might be an answer that helps this next question, but another great question from David Horton. If you could help address how strange performance issues during the sizing process in the context of drive projects. For example, if there's a basement space with no cooling load, a top floor space with high cooling load but little heating load, an open staircase and an elevator, how would you think about addressing these different issues in sizing?
You want me to take that? I know he was talking to me a little bit. He knows that I know the Riverside Drive projects. And so, like, they were a nightmare to deal with because they're straight up and down houses on the river. And they're like 4 stories above grade with a garage, tuck underneath garage. And then you have all the moisture blowing in from the river. So that's unaccounted for. And there was a bunch of anomalies that just made those things a nightmare to design for. One of the things that happened is, like, the designers that were working on them, they did not give enough credit to what was going on down there, and they didn't pay enough attention to each of the zones individually. So in a house like that, if I didn't get to design any of the Riverside Drive, but if I was doing it, I would have used multi-zoned heat pumps as my way to go, because I can put something different in every single one of those zones and still come out with something that's an affordable design. So that, like, those type of houses where we know they're going to be low load, these were inside the LEED program, so we know that they had to meet Energy Star requirements up front. So as long as the verifiers did their job and went out and verified that each one of the construction elements were being installed correctly, then we could count on that, and we would know that if it has a basement space with no cooling loads, then we need a heating plant down there that's mostly worried about heating, and we're not that worried about cooling. And then on the top floor with the high cooling load, we could put something in that could handle that and size away from the heating load and towards the cooling load. So being able to zone things and use these inverter heat pumps that allow you to use these different types of indoor equipment is a big bonus to houses like this.
Awesome. Thank you. So our next question comes from Nate the House Whisperer through YouTube. Is there a push to standardize SHR ratings at partial load? Do any OEMs offer this at a partial load and share that?
So I'll take a quick stab at that and say some of the OEMs are beginning with variable capacity equipment to show the performance at other than just full capacity. So some show max capacity and min capacity. That's what I see more often than not. But the problem that we've got here is there's a lot of OEMs that unfortunately don't provide us enough data to really be able to make good informed decisions about how that system's going to perform at lower reduced capacity settings. So in terms of SHRs and things like that, part of the language in the new Manual S is kind of got almost like a passive aggressive hint to it. Like, hey guys, we need more data. We need you as OEMs to provide us with the facts so that we know how this thing's going to perform when it's at other than full load, and we can actually make an intelligent, informed decision about this sizing and use this new criteria. So to kind of, quickly answer your question, we are inputting a lot of this new language with hopes that the OEMs will see and realize and it will start to come. Right now, unfortunately, many of them are not providing us enough data to be able to really make educated decisions on the low end of the operating spectrum.
I will say, pro tip, Mitsubishi, if you have access to MyLink Drive, they have, for not everything, but for a lot of these, they have their engineering data published. And if you go into the engineering data, there are part load graphs for their equipment that you can get in and you can decipher. Now, it's not straightforward, like here's what it's doing at this, that. You do have to know how to use, graphs and things like that. But if you get into the engineering data, there are engineering graphs in there for part load conditions that you can use.
Awesome. Thank you. So one more question from Rick Carter via YouTube. My house was originally built in the late 1800s, now uses gas with 11.5-foot ceilings. I could never get any comfort levels in heat mode with a heat pump. Any way to use one of the newer units to be able to address this more appropriately?
So I'll take an initial stab, Jeremy, and let you chime in. As Jeremy mentioned earlier, with an older home, one of the byproducts we often see, Rick, is that they're fairly leaky, fairly drafty, and that can make it really tough to keep things adequately warm in the wintertime. So I always tell people you got to start by addressing the envelope. So anything you can do to seal up, tighten up that envelope, improve insulation levels wherever practical. I mean, to me, before you go to any given type of equipment, no matter what it is, your first order of business really is work on the envelope. Once you work on the envelope, you're going to find that any type of system, of course, is going to perform better. And I know that's nothing that you don't already know. On the equipment side of this thing, when we're looking at cold climate heat pump sizing, variable capacity heat pumps, since I got kicked off the stream here and had to log back in, we lost a few minutes, and I was going to share a few slides on what we call the advanced heat pump sizing method. Unfortunately, the IT world didn't want that to happen today. But, what you want to look at here is we do now have an advanced heat pump sizing method. And what it's going to boil down to, and I'm going to really oversimplify this to shorten our discussion here in the sake of time, is there's a set of metrics, right? Sizing limitations or sizing factors using variable capacity equipment following this new advanced cold climate, if you will, heat pump sizing method. And we're going to look at not only max capacity limits, but also minimum capacity limits to make sure the unit's going to perform well and stay loaded up, as I mentioned, so we avoid some of those compressor failure issues and dehumidification issues and such. But at the end of the day, what you're going to find is when you follow the steps, there's 4 steps that you've got to follow. They're kind of detailed in the notes and the footnotes to the table. You've got to meet all 4 of these criteria. And the one that often in a cold climate type situation, which, maybe what you're dealing with an older home that's a little leaky as well, is we're not going to be able to meet all that 4 criteria. So then we got to go kind of like the flow charts Jeremy showed earlier. All right, this won't work. We can't meet the variable capacity advanced sizing criteria. So we've got to jump over here and use the variable heat pump advanced dry sizing criteria. So there's a whole new category that we didn't have before called the dry sizing criteria. And we've got to have a home that either meets the definition of a dry home, which very few of us probably live there. Maybe if you're up in high elevation in Denver or somewhere with low humidity, but for the most part, we're not going to meet that criteria. That's a home with a sensible heat ratio of 0.95 or greater. So that's going to be hard to achieve for many of us. But what we're allowed to do now is basically do active dehumidification to create a dry home. So to create the ability to use this dry sizing criteria. So now we can size the heat pump, guys, to meet the heating load, knowing that it'll have cooling capacity to drive down the sensible load, but knowing that we're going to struggle to dehumidify. So the new Manual S now addresses that. It will mean some additional form of equipment to meet that active dehumidification need. Now that could be a dehumidifier, that could be a ventilating dehumidifier, that could be some reheat type system, some other control strategy that accomplishes that. But if we can do an active dehumidification to meet this advanced dry sizing criteria, then we can truly size the heat pump to meet the heating load of that house. So I'll be quiet and pass it off to you, Jeremy, but that was something I didn't quite get an opportunity with the IT issues to show you my slides and talk more about this new advanced method.
No, you did a great job. I only have one thing to add. Your house might be a candidate for dual fuel. Like Mitsubishi has the IntelliCoil where you can match up any furnace with the outside inverter and still get the full benefits of an inverter heat pump and just use the backup heat as you need it. And then there's also just true dual fuel systems out there that have always existed. So like in a house like that, that's where I would go. I would not go 100% heat pump. I would do a little bit of gas with the heat pump as much as you can get out of it. I call it the most juice for the squeeze that you can get, and then switch it over to gas when you truly need that extra comfort.
Awesome. Thank you both. And for our final question, this comes from Tony M on YouTube. Do you know if the changes to ACA Manual S, aside from the read-only version on the website, will be released in an abridged version, or will the whole thing need to be purchased? Essentially, how can people start accessing this?
Yep, I'm going to be very honest with you. This is still a work in progress. So I have heard, as I mentioned earlier, that hopefully within the next couple of weeks here, it'll be available on their website as a free read-only version. They have somebody who is working on reworking the informative content so that there'll be a lot of examples and explanatory information to support the new normative rules and procedures, if you will. And when that is all complete, I know that they're planning to publish a brand new book where you can get the whole thing, the normative sections along with the informative and supporting example content in the back part of the book, which is the way it's set up now. I have not heard if they're going to provide, Tony, a abridged paper version that you can purchase at this point. I've not heard that answer.
Fantastic. Well, thank you both so much for answering all these questions. And with that, I would love to introduce our last guest, Brent Davidson, who will share a little bit about the Heat Pump Summit.
Awesome. Hey, everyone. My name is Brent, and I'm here to tell you about the Heat Pump Summit. It's a conference training event for contractors happening in Berkeley, California on November 13th. This event, 3 parts to it. There's a detailed training day, conference content, and trade show tables. It's important to note that this event does cover both HVAC and water heating. Quick run through some of the interesting stuff that'll be happening here. The training is really focused on covering from start to finish, from sales through commissioning. Folks like Larry Waters of Electrify My Home, he's going to be talking about successful business electrification. He's been doing heat pumps only for many years. Building engineer Ben Knopp, he's going to talk about detailed design. Really interesting live demonstration model, kind of correcting some common myths of basic fluid dynamics that affects HVAC. And MeasureQuick's Joe Medosh is going to be there, rounding that out with commissioning. Also, a REAM manufacturer training will be happening, and for folks out in California, that'll qualify you for the TechClean California's new heat pump water heater rebate. Conference content is all targeted at contractors, very tactical stuff. Bunch of strategies around like fitting new load into the electrical panel, emergency retrofit installs, successful strategies for that, both in air and water. Lots more to cover. Check out the heatpumpsummit.org website for the full lineup. And it's going to be a jam-packed day. Everything's really from that building science-based approach. And the goal of the event's just to make happy heat pump customers, size small for the grid, and meet other experts by attending the summit. We can give a discount for folks on this webinar, MQ100 for MeasureQuick. MQ100 gets $100 off. And we've got a great hotel rate, $139, DoubleTree on the San Francisco Bay. And more info, like I said, heatpumpsummit.org, and you can reach me, Brent, at heatpumpsummit.org. That's what I got.
Fantastic. Well, thank you, Brent. So we have covered a lot of ground today, from understanding the consequences of oversizing to breaking down the building envelope and diving deep into load calcs and Manual S. We all know applying these principles is the most challenging part by far. And our goal today was just to remind you of some of the foundation you've already built. But if there's one takeaway from today, let it be this: good design isn't just a nice to have, it's must have. So thank you to Anthony Maynor and Jeremy Begley and MeasureQuick, who brought a wealth of knowledge and experience to today's session. We really appreciate all of your time, as well as the time of our audience for the excellent questions and such an engaging time. So with that, we hope you will all join us next Wednesday at 11 a.m. for the next webinar in this series, and hope you all have a great rest of your day.
Thank you, guys.
Thanks, everyone.
Thank you, everyone.